Okay, let's dive right in. What if I told you that the 9, 10, maybe even more formulas you're trying to cram into your brain for vector calculus are, well, completely redundant? That there's actually one single concept, a master key, really, that can unlock every differential element you'll ever need? Seriously, forget the flashcards, forget the rote memorization. Today, we're going to replace that entire pile of formulas with one single, elegant idea. Does this look familiar? I bet it does. You've got your three coordinate systems, right? Cartesian, cylindrical, spherical. And for each one, you've got to memorize the formulas for differential length, area, and volume. That's at least 9 formulas, and let's be honest, it's an absolute nightmare before an exam. Yeah, we're talking about a serious case of formula overload here. It's a total flashcard nightmare that doesn't just waste your time, it actively leads to confusion and silly mistakes when you're under pressure. But there is a much, much better way. To find that better way, we've got to go back to the very basics. So just for a second, forget all the formulas and just look at this simple cube. This little guy is a differential element. Think of it as a tiny fundamental building block of space with sides dx, dy, and dz. Everything we're about to do starts right here with understanding this one little block. You see, the secret is to stop thinking about abstract formulas and start thinking about these differential elements as actual physical building blocks. Once you can visualize them, I promise the math becomes incredibly intuitive. So here it is. This is the mental shift that's going to make everything just click. From now on, I want you to think of these differential elements like Lego bricks. It sounds simple, I know, but it's a super powerful way to make this abstract stuff totally tangible. Let's break it down using that analogy. Differential length, or DL, that's like one of those tiny 1x1 Lego pieces. It just represents a single tiny step in some direction. Then you've got differential area, DS. That's like a flat plate piece, the kind you'd use to tile a surface. And finally, differential volume, DV, is your standard brick, the block you use to fill up a three-dimensional shape. See? Line, area, volume. And this brings us right to the core idea of this entire explainer. The one concept that unlocks everything else, the master key, is the differential length, DL. If you know DL, you basically know everything else. And hey, don't just take my word for it. This comes straight from Sadiku's Elements of Electromagnetics. The author literally tells us, just remember DL, and the differential area and volume can be easily found. This isn't some weird shortcut, it's the way it was meant to be done. Okay, now this slide is the whole ballgame. It puts the entire system on one page. Just focus on that middle column, the DL, master key. Those are the only 3 formulas you ever need to commit to memory. I'm serious. Everything else is just multiplication. If you need to get any differential surface area, ds, you just multiply the length components of the other 2 coordinates. So say you need the surface area on the xy plane, where z is constant. You just multiply the dx term and the dy term. That's it. And for differential volume, dv, you just multiply all 3 components together. This pattern works for every single system. It's that simple. All right, theory's great and all, but let's prove this master key method actually works on a real textbook problem. We're going to find the surface area of a piece of a spherical shell. So here's our object. It's a chunk of a sphere, and it's defined by these bounds for the radius r, the angle theta, and the angle phi. It looks complicated, I know, but with our method, it's going to be pretty straightforward. Our specific goal here is to calculate the area of that inner curved surface, the one labeled AEHD. The first crucial step is just to figure out which coordinate is being held constant for that particular surface. So if you look at the surface AHD, you'll see the radius r is constant. It's stuck at a value of 3. Now, since r isn't changing, that means our area element ds has to be built from the other 2 components of the spherical DL formula. What are those? They're r d theta and r sine phi and phi. We just multiply them together, and what do we get? R squared sine phi d theta dphi. That's our ds. No memorization needed, just a simple derivation on the spot. And here's the final step, beautifully laid out. We just plug in our constant radius, r equals 3, and then we set up the double integral using the bounds for theta and phi that they gave us in the problem. And just like that, the problem is now just a standard integration exercise. We derived the hard part in, what, a few seconds? Okay, so let's tackle the biggest point of confusion for pretty much every student. Those weird extra variables like rho and r sine theta that seem to just pop up out of nowhere in curvilinear coordinates. Where on earth do they come from? You know, when you look at the DL formulas side by side, it becomes super obvious. In Cartesian, a little step in the y direction is just dy. It's clean, it's simple. But then you look at cylindrical, and a step in the phi direction is rho d phi. Wait a minute. Why is there an extra rho there? It's not just an angle, is it? It's a length. So this is the key question we need to answer. These terms aren't just random factors thrown in to make your life difficult, I promise. They have a very specific and actually very important physical meaning. And here it is, the aha moment. On the left, in Cartesian coordinates, a step dy is just a straight line. Its length is dy. Simple. But look at the right, in the cylindrical system. A step of d phi isn't a straight line. It's an angular change. To turn that little change in angle into an actual arc length, you have to multiply it by the radius rho. It makes sense, right? The farther you are from the center, the longer that arc is for the same tiny change in angle. That's all these terms are. They're just conversion factors to get you from an angular change to a physical length. So there you have it. You've seen the problem, you've seen the core concept, the real-world application, and the most common pitfall. Let's wrap this all up into your new, super streamlined toolkit for vector calculus. Here it is, the derive, don't memorize method, boiled down to 3 easy steps. 1. Identify your coordinate system. 2. Recall that one single DL master key for that system. And 3. Just multiply the components of DL to get any area or volume element you need. That's it. You're done. So I'll leave you with this final thought. Using nothing more than that spherical DL formula we looked at, could you now set up the integral for the surface area of a complete sphere? The answer is absolutely yes. You now have the fundamental tool to build any of these formulas from scratch, whenever you need them.